Hi folks, and welcome to the Abstract Algebra Review. And as you see on the right hand side, there's a chat box, so if you have any questions along the way of what we're going to be covering, just let me know. Pop those questions right in there. And tonight what we're going to be taking a look at is the first isomorphism theorem and the fundamental theorem of finitely generated abelian groups. So that'll be our focal point. In particular, I'm trying to highlight a couple of topics that questions were asked about earlier. So let's get started. We want to find a subgroup H of the integers such that Z mod H is isomorphic to Zm, direct product with Zn, or explain why no such subgroup exists. So what happens a lot of times when we see these abstract problems, we freak out, and what I'd suggest, and you'll see me do it a couple times tonight, is actually try and work with some examples. So let's assume for our example we'll take Z into, let's say, Z3 some Z5 for example here. Now if we want to do this, if we want to try and find a homomorphism that does that, what's kind of the natural way to go? Well, if you have phi of x, well, what this should look like is most likely x mod 3, and then in the second coordinate maybe x mod 5. I'm not saying this is going to work for sure, but we can see. And so there's some questions that should be popping in your head. The first question, is it well defined? Okay, so is this actually a well-defined mapping? What does that mean? Well, it means if x equals y for x and y being integers, then does essentially phi of x equal phi of y. So this is usually glossed over. A lot of people don't pay attention to it, but it's actually quite important. And in this result, what do we have? Well, for phi of x, notice that would be x mod 3 and x mod 5. And for phi of y, notice you have y mod 3 and y mod 5. There's a caveat here. Notice in the integers, if x and y are equal, that means x mod 3 equals y mod 3. And we have x mod 5, since x and y are equal, that should equal y mod 5. Another way for me to have written that, I could just have written x is congruent to y mod 5. And same thing, x congruent to 3 mod 5. But since those two are equal, we have that order pairs equal. So it is well defined. Now let's try another. Let's say we want to look at phi of x plus z. So I'm getting a little bit lax here, but we're dealing with an example trying to see what happens. So if we have phi of x plus z, what are we actually looking at in that case? Well, we should get x plus z mod 3 and then x plus z mod 5. But notice this is the same thing as x mod 3 and x mod 5. And the way we've defined our operator for addition, we do it component wise. This is z mod 3 and z mod 5. So notice we get that this is just phi of x plus phi of z. And so it seems like we have a homomorphism here. Right? Everything's hunky-dory. Now, are we on to? Okay, so is phi on to? And with the question here, what do we need to look at? Well, all we need to do is just try and determine, okay, if phi is on 2, we need to find any, let's say AB be an element of Zm, direct product with Zn. Okay, so then what happens? Well, if that's the case, we need to find something that produces A and B. So that means essentially we have to find some integer that does this. Well, think about what happens if we have M, A being in Zm, so A mod M, and we have B mod N. Okay, so that means A is equal to some MK plus A, or I shouldn't write A. Let's rewrite this. Oh, I'm sorry, I went to M and N. Let's do 3 and 5. I was getting a little ahead of myself here. So 3 and 5. If I go A mod 3 and B mod 5, and then we'll be able to generalize this a little bit more. So this would mean, in the first case, we're writing it as some 3k plus A, and in the second case we'll write it as some 5l plus B. Does there exist an integer such that that occurs? Well, let's think about this. We need essentially some multiple that gives us A and B all at the same time when we kind of divide out here. So what value would do this? Well, any multiple of 5L, any multiple of 3K plus A. Well, think about this. If we wanted to maybe break this down further, let's go through some cases. So say we had 1 mod 3 and 4 mod 5, right? There's actually a nice theorem that has us combine these in a nice way. So if this is the case, how do we break these down further? Well, we need x congruent to 1 mod 3 and x to be congruent to 4 mod 5. Does there exist such an x? Right, well, let's think about it. Well, look at the multiples of 3. You'll have 3, well, for 1 mod 3, you'll have 1, 4, 7, 10, so on and so forth, right? And in the other scenario, you'll have, well, notice we have 4, then 9, then 13, and so on and so forth, right? But what happens is, in this case, where we have x congruent to 1 mod 3 and 4 mod 5, our magical value in both cases was 4. Well, how do we get that? Well, that became, we needed a 3k plus 1 and a 5l plus 4. And the idea behind this is essentially what allows us to solve, and we haven't quite mentioned it in class, but you can see, look up the Chinese remainder theorem. That says there'll always be a solution to some system of this type when you have these things not having much overlap here. Okay? So, let's move this on forward. Alright? So in general, you could write this as A, 3 plus A, then we would have 6 plus a, 9 plus a, and 12 plus a. And for the b, notice you'd have, to kind of give you an idea, you have b, 5 plus b, 10 plus b, and that should be it for that list. And now why don't I have to go any higher in my list? Well, notice the least common multiple of 3 and 5 is equal to 15. So what's going to happen, the Chinese remainder theorem says basically that you have something between these two lists that have to be in common. Okay, and wherever that occurs, so some common pair or a common element, called x, and this is our choice in the integers. So then you'd have phi of x essentially equaling a mod 3 and b mod 5. We have our solution there. Alright, so now hopefully that lets you know. So the Chinese remainder theorem, as I said, kind of doing a little bit of hand waving there, but that's an important result that we can kind of use. Now what happens from here? Well, you have the first isomorphism theorem. We have a homomorphism, it's on 2 in this case. What does the first isomorphism theorem state? Well, it states there exists isomorphism from Z mod the kernel of phi to this Z3 direct product with Z5. Okay? So if that's the case, then now what happens? Well, since we have that, our first isomorphism theorem, what happens in general then, as long as we can find kernel phi, we have a solution. So what is kernel phi? So kernel phi in this case equals what? Well, if we get an idea, it has to map to basically a multiple of 3 and a multiple of 5. So we want it to be 0 mod 3 and 0 mod 5. So what elements actually do that? Well, this, or I shouldn't write kernel phi equals there, that's a little... Let me be careful here. Kernel phi is a set, so we'll say x such that x mod x is congruent to 0 mod 3 and x is congruent to 0 mod 5. Okay? So notice what happens now. Well, if you have x congruent to 0 mod 3 and x is congruent to 0 mod 5, when does that occur? Well, if it's a multiple of 3 and multiple of 5, that means it has to be a multiple of 15. Okay. So if that's the case, then, well, we found all of a sudden that we have our nice results, right? So we actually can say, in that case, you have Z mod 15 is isomorphic to Z3 direct product with Z5. Now what we want to do is extend this. Can we go further? Well, most people say, okay, I did for one example. That means the rest must hold as well. So you can take a look at another and see what happens. But in general, there are a few things that will happen. We can change this proof just slightly, and did a little bit of hand waving with that Chinese remainder theorem, so I want you to be careful with that just to see what's going on. There's a reason I can use it here. I had a nice property where 3 and 5 are relatively prime. That doesn't hold in general. So in general, there's other cases to consider. For example, let's say we were mapping into, say, Z6 and Z4. Right? Does the same, let's look at the kernel first. If we did the same thing where we did phi of x is equal to x mod 6 and x mod 4. What is the kernel phi in that case? Well, that would be the x congruent to 0 mod 6, and also, x such that x is congruent to 0 mod 6 and x is congruent to 0 mod 4. And you might say, oh, well, that should be nice and easy for us. And then when you start to think about it, it's not 24 anymore. Well, what is our answer? Well, in this case, it has to be a multiple 6 and multiple 4, the least common multiple. So the LCM of 6 and 4 would equal 6 times 4 divided by the GCD. I know you can do this in your head, but in general, that's what we want to build to. So that's going to be, you have 2 for the GCD, so this will be 12. So this set would equal 12. Okay? Now, can you map to every element? That's another question. What do I mean by that? Can you have an onto map? So is this onto? Is phi onto in this case? And so last time I kind of skimmed it. This time will be a little bit more careful. So notice everything leads up to 12. Let's see, what would that look like? So if we have AB being an element of Zm, direct sum with Zn, notice what that means is we have A mod n, or A mod in this case, switching M and N to 6 and 4. So you have A mod 6 and B mod 4. Right? Can we always find an X that when we divide it by 4 and 6 you get those values? Well, for every single possibility here, the difference is these two are not relatively prime. So let's take a look as to what some of the values are. So first off, you'd have A and then 6 plus A, but notice as soon as we're at 12 plus A, we're just doing a repeat of this. So that isn't going to give us any more values. So you have B is our other one, and in that case we have 4 plus B, and then we have 8 plus B. Okay. So now, if A equals 1, and B equals, oh, let's say 3, notice, in that case, you'd have X equals 7. Because when you do 7 mod 6, you get 1. And when you do 7 mod 4, you get 3. So it might seem like, oh, this is always going to work. Well, if A equals 1, and let's say B equals 2, what happens? Well, notice your one list actually becomes 1 and 7. Your second list of values becomes 2, 6, and 10. Notice there's no values in common. So is it possible to have that? Well, no, it's impossible here to have that in our list. And if you don't believe it, here we can try some more. You could try 12 plus A, and notice we'll see what happens here. So you have 12 plus A, then 18 plus A, right? Let's see if maybe there are repeats here. In the other case, you'd have 12 plus B, 16 plus B, and 20 plus B. Notice what happens. If you plug 12 plus A, you get 13. In that case, for A equals 1 and 19. Well, all of these are going to be even values here. So you have no possible overlaps. And no matter how long we continue this over and over and over again, you're not going to have any overlaps. And the Chinese remainder theorem does have this requirement that these two values have to be relatively prime. So we're running into trouble. And so I know I spent a lot of time on this problem, but is it always going to happen? Or explain why no such subgroup exists. So the thing that we're going to need in this case is need M and N to be relatively prime. Okay? And this is a big part. I mean, the reason I'm taking the time to show you some different examples is because this is how we build to some bigger theory. So we run into a problem with that map, but if M and N are relatively prime, we get something nice that happens. And this is going to lead into that fundamental theorem of finitely generated abelian groups, kind of working with the prime factorization and whatnot. So there is ways to build on this other case too, but we're just going to focus for right now on M and N being relatively prime. So if this occurs, so this is the extra caveat that we're tossing to this problem. Let phi, so here's your sketch of your proof. Let phi map Z into Zm direct sum Zn. And once again, we'll remember M and N are relatively prime here, where phi of x equals x mod m, comma x mod n. Okay, so what happens from here? Well, notice phi is well defined. Since for x, y in the integers with x equal to y, we have x is congruent to, if they're equal, that means they're congruent mod m. X is congruent to y mod n then. And if those two hold, that means x mod m, x mod n is the same thing as y mod m and y mod n. So we have a function, basically. We don't have something map into two different elements at once. Okay, so that's good. So now, since it's a function, we got to show it's a homomorphism. So in our homomorphism case, we'll let let's say R and S be integers. Then phi of R plus S is equal to R plus S mod M and R plus S mod N. Okay, now moving forward from here, where do we go? Well, you can break this up into R mod M, R mod N, and then whatever our plus symbol means in our direct product essentially, or our Cartesian product, and this will be S mod M and S mod N. Okay, but this is the same thing as just phi of R plus phi of S. Well, what does that imply? Well, then we have, therefore, phi is a homomorphism. For the onto part, okay, consider an element AB in this direct product. Now, by our Chinese remainder theorem, so if you don't know what that is just yet, I can break that down for you in class or whatnot, or by the Chinese remainder theorem. We know that there exists an x in the integers. In fact, you could even put it in ZMN, in that case, since they're relatively prime. But there exists an x in the integers such that x is congruent to A mod M, and x is congruent to B mod N. Hence, phi of x is equal to x mod M, x mod N, which is equal to the same thing as A mod M and B mod N. Okay. So last but not least, let's try and show that the kernel of phi is equal to this set that's generated by the least common multiple of m and n, which in this case is going to be m times n. So assume x is an element of kernel phi. Then phi of x is equal to 0 mod m, 0 mod n. Notice now, in this case, what happens? Well, x equivalent to 0 mod m and x equivalent to 0 mod n implies x has to equal the least common multiple of m and n. Therefore, x is an element of the set of the set generated by the least common multiple of m and n, which in this case, since they're relatively prime, it is m times n. Once again, but just to generalize, I want you to be able to generalize this thing. So you want to try and generalize to just what would the kernel always be, and you can always see it's this least common multiple there. Now, moving forward from this spot, how do we actually show that this set, so we know that you have containment one way, the kernel phi is inside the set. How do we know that the set equals the kernel phi? Well, for y in the least common multiple of m and n, I wrote that backwards, but no big deal. Oh, and I should say the set we find, well, what happens? That means y is some multiple. So you have k times LCM of m and n equals y. Therefore, when you reduce that down, you get y is congruent to 0 mod m, because it's a multiple of m, and y is congruent to 0 mod n. Hence, phi of y is equal to 0 mod m and 0 mod n. And so then, what do we have at the end of the day? Well, you have that y is an element of kernel phi. So you've now shown that those two sets are equal. Okay? Finish this off. All we have to do is use the first isomorphism theorem. So by the first isomorphism theorem, we know that the integers modulo this least common multiple of m and n, sorry for it being extended here, has to be isomorphic to this direct product that we were talking about before. Okay. One key caveat though, we're using m and n to be relatively prime. Okay, so we added that in, that little piece, just so we could kind of work the problem. Alright, hopefully that makes sense, but what this does lead to is a much bigger theorem, and that's what we were kind of working this problem for, so you can get an idea as to where we're headed. So that leads to the fundamental theorem of finitely generated abelian groups. And to start, basically you start trying to describe things as direct products. Now we could talk about internal direct product and external direct product, but remember, if they're finite, we are going to have some isomorphisms there, so not too concerned on which approach we take. But remember, this is the multiplicative group. So to look at the elements, obviously 1 will be in there. This is the identity. 2 is relatively prime to 15. 3 is not. 4 is. 5 and 6 are not, but 7 is. 8 is relatively prime. 9 is not. 10 is not, but 11 is. 12 is not, but 13 and 14 are. So the fundamental theorem of finitely generated abelian groups tells us this, well, if there's 8 elements here, so this has 8 elements, the possible isomorphisms, so possible isomorphisms. You have, remember, 8 is just 2 cubed. And you can look at the partitions of this number 3 up here, and that's going to tell you how this can break apart. And the partitions of 3 are 3, 2 and 1, or 1, 1 and 1. And partitions, just how many different ways can you sum up positive integers and get 3, and 2 plus 1 equals 1 plus 2. They're the same partition in this case. So what that means is the possible isomorphisms that we have are, in the first case, if it was all of that 2 cubed, you'd write it this way. So z of 2 cubed, which is the same thing, here's z8. The second scenario, you do z of 2 squared, and then since you have the plus, we'll put that little plus symbol right there, and then this is 2 to the first, so that's the same thing as z4, direct sum with z2, or direct product, whichever you want to call. In the last case, we have everything's a 1, so it's just this direct product of 3 z2s, 3 copies of z2. So what happens here? Now there's a few nice theorems in your book that actually discusses how to break this down even further, but we'll actually go through it the long way just to give you some intuition. So we'll write down the element in the order just for us to see as what's going on here. So remember, this is multiplicative. So the element 1, that's not really going to tell us much information because that has order 1, and we should have something of order 1 in each of these. It's going to be the identity element. Now the element of order 2, just so we know, remember we have 8 elements, so that means the order will have to be 2, 4, or 8. So notice 2 squared is congruent to 4 mod 15. Now the next one we have to check is 2 to the 4th. Notice that's 16, which reduces down to 1 mod 15. So this element has order 4. Okay, 4, if you notice, 4 squared is equivalent to 1 mod 15. So we get 1 right there. And you don't have to list these out. I'm just trying to do this to illustrate. For the 7, notice 7 squared, what is that going to be equivalent to? So you have 49, and then 45 is the next closest, so that's going to be 4 mod 15. And here's where we can kind of use some nice intuition. 4, we notice when we square that, we get back to 1. So 7 to the 4th is the same thing as 4 squared, essentially, which is equivalent to 1 mod 15. So just playing with the nice properties of our modular arithmetic. Similar manner for 8. So 8 squared is going to be 64, but notice that's 4 mod 15 because you can basically 15 times 4 gives you 60, and then you add another 4, that's how you get 64. So that means 8 to the 4th is the same thing as 4 squared, because we squared both sides of this previous one, which means this is going to be equivalent to 1 mod 15. Okay? Now when we get to 11, a little bit higher, but 11 squared, the way I'd like to think of that, that's the same thing as negative 4 squared, so that's going to be equivalent to 1 mod 15. There's this has order, oh, I wrote 8 has 1, that should be 4. 11 has to be then 2. 13, we'll try and write over here, 13 squared is the same thing as negative 2 squared, which is the same thing as 4 mod 15. And so what does that mean? Well, when we go 13 to the 4th, that's the same thing as 4 squared, which is equivalent to 1 mod 15. So 13 was order 4. And last but certainly not least, we have 14, and notice that can be written as negative 1. When you square negative 1 you get 1, so that's 2 is the order there. So when you look at these elements though, the bottom set has all elements of order 2. Right? Because if you go 2 times any coordinate, you're going to get back to 0. So that means this set is out. Okay? And on our other one, this has at least one element of order 8. In particular, 1. You can actually do a lot more than that, but 1 does the trick. It's an element of order 8. There's no elements of order 8 in our list of the elements of Z, the multiplicative group Z15. So this one's out. So what does that leave us with? Well, we don't have to go through a whole bunch of guess and check work. We actually have, and you might recognize this from a previous section, that this is isomorphic to the direct product of Z4 with Z2. Okay? So that's a nice result for us, and we can start to build upon these things, right? We can build bigger sorts of notions as to what's happening with all these sets. But notice we could eliminate a lot of possibilities right out the gate just by doing the orders. Now, we could have dealt with subgroups, we could deal with all sorts of different things to get our answers, and we can even do it in a more immediate fashion, and hopefully we can build upon that notion coming up soon. So first off, there's some nice results in your book that actually talk about this. In particular, existence of subgroups. You have a corollary. So does every abelian group of order 45 contain a subgroup of order 9? You have a corollary that says yes, this holds. But just to elaborate, possible abelian groups. So 45, if you recall, that's 3 squared times 5, right? So that means, and when they're relatively prime, you can combine them in whatever format you want. So you have z, and then we could break it apart if you want. You could write it as 3 squared direct product with z5. But what there's a nice little result that says if they're relatively prime, which in this case they are, you can combine them all into one. So that's z45. Okay. Either way, whichever one you want to work with, that's fine. And the 3 squared I'm just going to write as 9 from here on out. Now the other possibility is we could break 9 apart. Right? When we partition 2, you can partition it into just 2 or 1 plus 1. And the 1 plus 1 case would be the z3, some z3, some z5. Now if you wanted to, some people get fancy with it. They combine one of the z5s with the z3s, and so they write this as z3 direct product with z15. Right? Either way, it means the same thing. Now, if you're wanting to see it, you can actually do it out. In the way I would go about it, for the subgroup of order 9 in the second set, I'm going to work with the one on the left. We're just going to let it be the subset of elements A, B, 0, such that A and B are elements of Z3. Notice that means you have 3 possibilities in the first coordinate, 3 possibilities in the second coordinate. Notice you get 0, 0, 0, so you have the identity. And then basically this is isomorphic to Z3 some Z3, which has 9 elements. Done. Right? In the other case, all we need to do is, same song and dance, we'll just let it be A in 0. And if you wanted to, if you want to work with this one, I mean, it's just as easy. You have this be the cyclic subgroup generated by 5, essentially. And in this case, it's A0. We're just letting A be an element of Z9. Okay. You can check. Not too hard to see that both of these are subgroups, and you have your answer right away in terms of what's going on there. We can write these too, by the way. So we could write, if written the first case, cyclic subgroup generated by 5. You could have written this as the cyclic subgroup generated by A0. Or, in fact, if I wanted to be specific, 1, 0. That's a parentheses right there. That would do the trick. In the second case, we have 2 generators, so you'll have to do something like 1, 1, 0. And the second, or let's do 1, 0, 0, sorry. And then in the second case, we'll do 0, 1, 0. We could have dealt with 1, 1, 0 and kind of worked our way around that, but if you use those 2 as generators, you'll get the 9 elements that way. So just this way, you've seen a few different methods for actually writing that out. Now, does every abelian group of order 45 contain an element of order 9? So that's a totally different question. In the first case, so notice you have Z9, the element, so in, let's say, Z45, we had that element 5 there, right? So we had order of 5 equals 9. Don't confuse that with absolute value or anything like that. Or similarly, if you preferred the Z9 direct product with Z5, the element 1, 0 has order 9. Now, look at the second case. However, Z3, Z3, Z5. what order will the elements have? Well, 1 if it's the identity, right? The 0, 0, 0. So just so you can see, you'd have 0, 0, 0. Right? Notice, if we did 1, 1, 1, what does this have for its order? Well, that jumps, right? So you get, if you go 3 times this, you'd get 0, 0, and then you'd have 3 in that third coordinate. So 3 is not a possible order. If you'd go 9, you'd get 0, 0, and then 4. But that's not a possible order. So our next possibility, if it's dividing 45, it has to be 15. And in that case, you get, oh, and I forgot 5, my apologies. 5 would be 2, 2, and 0, which is also not working. 9 didn't work, so now we move to 15. When you go to 15, what happens? Well, you get, in that case, you'd get 0 in this coordinate, 0 in the second coordinate, and 0 in the third coordinate, so this thing has order 15. So 15 is a possibility. 5 is a possibility if you go the order of 0, 0, 1. Right? You have that element has order 5. And then 3 is a possibility. If you notice, you can do 1, 0, 0, or 0, 1, 0, or even 1, 1, 0. All of those have order 3. But there is no element of order 9. And the reason why is Z3 some Z3. You cannot go up to 9 with that being your direct product in those first 2 coordinates. So since 9 is not available, so does every abelian group have an element of order 9? No. And then here would be your counterexample. Right? And if you're looking, I mean, you have the order of any A, B, 0, where A and B are not the identity. Say mod 3, then that has to have order 3. Right? That's the big component that tells us that nothing else is going to work. Okay, so be careful, understand that difference between what it means to be a subgroup of a certain order versus an element of a certain order. I know we talk about this and it seems kind of silly, but the real reason why, in the first case we have a cyclic group, in the second case we don't. And once we have that this is not a cyclic group, we have some different properties holding. But subgroups will still hold. You'll always have subgroups that of order that divide the group when we have abelian groups, what we're looking at. So how many abelian groups up to isomorphism are there of order PQR, where P, oops, that should be multiplication of order P times Q times R, where P, Q, and R are distinct primes? Well, we know that GCD of P, Q, and R equals 1. Hence, this nice little direct product is the same thing as Z of PQR down below, and you can break it up in multiple ways. You can do Z of PQ direct sum, ZR, which is isomorphic to Z of P direct product with Z of QR, which is the same thing as Z of Q and Z direct product with Z of PR. Sorry about that. So all of those are isomorphic to each other. And that's all the possibilities in our list. So what does that mean? How many abelian groups are there? Fundamental theorem of finitely generated abelian groups tells us this is going to be 1. So nice easy part when we have distinct primes and you're just doing all the first power. It does get a little bit harder though, but not too bad. When we have P1 to Pn being distinct primes, and we want to find how many abelian groups are there of a certain order here. So the possible groups, and then I'm going to write up to isomorphism on this one, but I won't on the next. Of order P1 to the fourth, right? Now, if you're struggling, say this scares you a little bit, well, let's do something a little bit easier. Let's take a look at Z2 to the fourth. Okay, so notice we mentioned the partitions of 4. So you have 4. We mentioned partitions earlier. It was partitions of 3, I believe, is the one we were dealing with. So we have 4 here. Another way you could break it up is 3 and 1. Another way you could break it up is 2 and 2. Another way you could break it up is 2, 1, and 1. And then you could do 1, 1, 1, and 1. So notice our different isomorphisms are Z16, which notice that comes from, let's write it out with the power here just for kicks, 2 to the fourth. The next one would be Z of 2 direct product with Z of 2 cubed, or 2 cubed. I know I wrote it in a different order. No difference if I switch. If I go 3 and 1 or 1 and 3, same difference. Next one, if we do Z of 2 squared, direct product with Z of 2 squared. Next one after that, we'll do Z2, we'll do the first power, we'll do another one of the first power, and then we'll do the direct product with the 2 squared again. And then the last one, just a direct product of 4 Z2s. So my question is, was there anything special about using 2 as our prime? Well, no. So the possible groups up to isomorphism of order P1 to the fourth, first one we have Z P1 to the fourth. Second one, we'll do Z of P1 direct product with Z of P1 cubed. Third one, Z P1 squared direct product with Z P1 squared again. Fourth one, Z P1 direct product with Z P1 direct product with Z P1 squared. And last but certainly not least, you have Z P1 direct product with Z P1 direct product with Z P1 direct product with ZP1. Okay, so that's the case where we have order P1 to the fourth. Now notice it all boiled down to this partitions of 4, because that's just our exponents on all these P1s. The same rules are going to technically apply, so the possible groups of order P2 to the fourth, right? My claim is we can figure this one out as well. So you have, in this case it goes P2 to the fourth. We can do the same thing, Z of P2 direct product with Z of P2 cubed, Z of P2 squared, and then direct product with ZP2 squared, then ZP2 direct product with ZP2 direct product with ZP2 squared, and then finally ZP2 direct product with ZP2 direct product with another ZP2 direct product with another ZP2. I should be saying P sub 2. And so we continue this process till we get to the possible groups of order Pn to the fourth. Well, notice in this case it's basically the same song and dance, except we're using n as a subscript instead of 1 or 2. So same song and dance. almost there. ZPN, direct product with ZPN, direct product with ZPN squared, and then finally the direct product of the 4 ZP P sub n's. Okay, finally. Now we're ready to rock and roll. Well, think about this. What can we do with this first group? Well, we can pair that. We got to pair with direct products with each of these. So we can pair it with that one, we can pair it with that one, we can pair it with this one, we can pair it with this one, and we can pair it with this one. And notice this one we'd have terms in between. So we'd have here, you can pair that with this on down, and each one has 5 different terms in each part. Until we finish off, we can always pair back into any one of these. So think about it. How many choices do you have in the first column? Well, you have 5 choices. Right? In the second column, you're going to have 5 choices again. And so we multiply that by the multiplication principle. Third column, we'll go to that and we'll get another 5 choices. You keep on multiplying because we're choosing one from each of those steps until you get to the last one, and there's 5 there. And now, how many times are we multiplying these things? Well, it's n times. Okay? And so what we finish with is 5 to the nth power. Now, if you don't believe it, try when we started the test, let's do 2 to the 4th, and let's say, just to keep it a little bit different, 13 to the 4th. Okay, you should test, and that should end up having 25 different groups of isomorphism. But now we've generalized all those ideas, and hopefully that'll be useful to you come time when it comes to the homework. All right. Last but certainly not least, let's try and take this and get some of those weird abelian groups that might be sitting out there, and showing that this is going to work out for us. So in terms of what's happening here, let G be the group of all n by n diagonal matrices with plus or minus 1 diagonal entries. So first off, let me kind of show you what we mean. Let's let A equal 1, negative 1, positive 1, and then 0, 0, 0. So I'm going to start with 3 by 3. And B equal to negative 1, negative 1, positive 1. And if we have zeros down the diagonal, first off, notice AB, what's going to happen? Well, you don't have to worry about all the matrix multiplication, because diagonals, you really just have to, if it's a diagonal matrix, you just multiply straight across the diagonals and you're done. So negative 1, positive 1, and positive 1 should be our solution here. And notice that is the same as BA. So this is telling us it's abelian. Right? And how many different combinations can we have? So what is the order of G when dealing, so I'll put order G, when dealing with 3 by 3 matrices? Well, let's see. Okay, so you have how many choices for here, for your top left entry? That would be 2 choices. How about this one? Well, you have another 2 choices, plus or minus 1. In this one, you have another 2 choices. So in this case, what do we have? Well, we have, this should be 2 cubed for the order of G. Now for this case, And you might be wondering, is it addition or multiplication? It is multiplication, because notice if you add two diagonal matrices of this type, you don't get another diagonal matrix with plus or minus 1 as entries. So that's why it's multiplication. So for this case, what happens? Well, we have if A is an element of G, then what does A squared equal? Well, notice you're squaring each of the diagonal entries. So if it's plus or minus 1, all of the entries are going to be 1 down the diagonal. So that means this is the identity matrix. So all non-identity matrices have order 2. Well, let's think about that a little bit more. Well, we have an abelian group, has order 8, right? So the possibilities would be, in this case, Z8, Z4, direct product with Z2, or the direct product of Z2 with itself 3 times. Oops, that's a 2. Okay, but everything in here has order 2. Well, Z8 has elements of order 8, so it's out. Z4, direct product with Z2, that's out because you have an element of order 4. There's elements of order 4. So our answer in this case, G is isomorphic to the direct product of 3 Z2s. But now that didn't answer the problem. It asked all n by n diagonal matrices. So let's build to that. So notice, first off, it gives us some intuition as to what we might be expecting here. So and we'll sketch this out. Let G be the group of all n by n diagonal matrices with plus or minus 1 diagonal entries. Okay, so what can we do with this? Notice the order of G has to equal, well, you have 2 in the first entry in the 1, 1 position, then you have 2 possibilities, or I didn't mean 2 as in the number, but 2 possibilities in that first position in 1, 1. And the row 2, column 2, you'd have 2 possibilities. In the third row, third column, you'd have 2 possibilities, and so on and so forth for each of those n. And multiplication principle tells us the order of G has to equal 2 to the n. And for A and B being matrices in this G, we find AB equals BA, since multiplication, this does not hold in general, but the fact that they're diagonal matrices. So hence, G is abelian. Okay, so we have its abelian. That means it has to be isomorphic to one of the abelian groups in our list. Now, here's the other caveat. Also, for A with AII denoting the ith row and column of our A, we find A squared has the ith row and column given by AII squared, but we know that's either plus or minus 1, which equals 1, since AII equals plus or minus 1. So hence, down the diagonal, and notice we didn't have to worry about the others because they're all 0. Hence, A squared equals the identity matrix. Therefore, all matrices in G that are not the identity have order 2. The only abelian group with this property is Z2, oh, we'll write it this way. We want our direct product where this is n times. There's other ways to write this too, by the way. So therefore, G is isomorphic to Z2, Z2, and direct product with Z2, and this is n times. So I know I took a little bit longer than usual for a lot of these problems, but I wanted you to mainly see how we can construct proofs, work through examples to try and get an idea of what's happening, and hopefully that gives you some answers to some questions. So if you do have any more, please come to class with those questions on Thursday, and hope you have a great night.